Lecture 17, lead derivative of one form, this case one form omega, and this is a component omega sub I. Now, we begin to consider the lead derivative of a scalar, okay? The scalar function f is omega I, vi. You see here I is, in this case, is a dummy index. So this is a scalar quantity. Now omega sub I is a one form covector field. They are covariant in this case, okay? It's a covariant variable because I here is a lower index. Vi is a vector field, contravariant. Vi here, it belongs to the tangent vector space, okay? And omega I belongs to the cotangent, okay, space or dual space. Now, U, vector U, is a given vector field, components U, K. This is a U that it defined along which we compute the lead derivative. Step 1, let's mark here, see? Step 1, start with a scalar function, omega I, vi, and apply the lead derivative, okay? Let Lu, omega I. You see, you just develop this expand, you see? This if vi, lead derivative of omega I, sorry, this I here is lower index. This is I here, is lower index. So this is vi, lead derivative of omega I, y, this case omega I, the lead derivative of vi, where this we already did before. The lead derivative of vi is uj partial vi respect xj minus vj partial y respect to xj. So this is a lead derivative of, in this case, okay, this is a covector vi. Omega I, you see, this belongs to the cotangent space, vector space, and vi belongs to the tangent vector space, is a vector. Omega I is a dual, okay, it's a covector, just for you to see. I'm repeating, okay, this definition, what we did before. Now, here is step 2. Expand the derivative, okay? The derivative u, this is attention, this is a function, this is a scalar, okay? You expand, this is vi, the derivative of omega I. This omega I, attention now, you see over here, in this case, you have Lu of vi, you see? Lu of vi, I just substitute over here. So, the derivative of this scalar function is vi, the derivative of u of omega I. This is, I just substitute this here, over here, okay? And remember that I here, with I here, they are dummy. So I can substitute, okay, by k. You see, the green letter tells you how this appears, this omega k, okay, that's uk. You see, the green one k, the green one I. You see, that's clear because it's a dummy index. So this is a relation 1. Now, then I can write, okay, I can expand, on the other hand, the lead derivative of this function f, okay? This is uj partial xj omega I vi. You see, I just applied the definition okay, of the derivative of u, lu of u. So that's quite easy. This is my function f, okay? This is f over here, this is f over here. Now, this, I can expand this uj, vi, partial omega I respect to xj, plus uj, omega I, partial vi respect to xj, wi. You say, sorry, I repeat here. So that's it. Now this is equation 2. Now, you see, this is from equation 2, and this one from equation, in this case, equation 1. So that's a set. Equation 1 is identical, is equal to equation 2, which implies, okay, this is the left-hand side, this is the right-hand side. This equation 2 is just over here, and equation 1 is just on the left-hand side. Now, I can cancel, see, uj, partial vi respect xj, this uj, this case, times omega I can cancel these two terms. So, from here, this leads to vi, you see, this is a parenthesis, okay? I just set this term on the left-hand side with a minus sign, which is over here. Now, vi here, that multiplies all these parentheses. This is equal to 0. Since vi is different from 0, you see, then I can write the derivative of omega I is equal omega k partial uk respect to xi plus uj partial omega I respect to xj. Now, look how interesting. If you compare the Lie derivative of this on this covector, okay, and compare the Lie derivative of the vector component, this is minus sign, okay, over here, and this is plus sign. Just an observation for you. You see, that's a derivation of the Lie derivative of a covector, okay, omega I, just there.